Hi, everyone. I'm Alfredo. I'm a director of engineering at Hearst, which is a media company with more than 360 businesses. And its major interests include magazines, TV networks, newspapers, and more. And some of the properties that you might be familiar with are Cosmopolitan, Esquire, and Elle. But there are a lot more. In total, we have 100 and plus websites, and they're all being powered by one application. It's great because it gives us a lot of control, but we have the additional responsibility that when we break something, it affects 100 and plus websites, and that's really bad, especially when it deals with performance. So for us, performance really matters. And today, I would like to share a few technical tips that we've done in the past, are doing, and are planning to do to speed up your websites. But most importantly, how you can embed performance into your culture, because you can do all of the stuff that I'm going to show you today, make your website really fast, then a few months pass and everything goes back to where it was before. So to me, it's the most important part of working on performance is how can you make it last? How can you make it stay fast after that you work on it? So the reason why performance matters, and this varies depending on what you're working on, but mainly is because people don't have patience. And if something is slow, they just leave. And for us, we found that the sweet spot is around 2 to 2.5 seconds. That's when most people feel like they're waiting, and that's just how humans perceive time. After a second, we switch to what is called passive time. And after humans enter passive time, we overestimate time by 36%. So anything that you can do, be that animations or something to keep someone engaged in active time, the more that they're gonna feel like they're waiting. So without showing anything, we can see that here before our median page time was around 9 seconds. I don't know if you can see it, but it's 9 seconds. And we can see that at 2 and 2.5, there's a drastic up of people just leaving because nothing of value is being shown here. So that's our goal. We needed to have something valuable shown around 2 and 2.5 seconds on a mobile, on a 3G connection. So where do we start? How do we start getting stuff done? And the main approach that is mostly advocated by performance advocates is to get the executive buy-in. And what this means is how do we convince our bosses, the executives that are making the decisions of where do we spend time, to put away some time for performance. And what you can do is first you have to measure. You can't optimize anything if you don't have anything to compare it to. Using web page tests, which is open source, you can run your site and see how it performs on different devices with different connections, be that a mobile on 3G or 4G or desktop with Wi-Fi or slow Wi-Fi. And a good tip that you can have is that with a small script, you can see how your website performs without third parties and with third parties. So you can compare how much you can control and make faster and what's something else that you are bringing in because they're helping you, giving you some revenue or something else, but you can compare that performance effort. Also, you can use Lighthouse right from the Chrome DevTools and also as a node module to just give you some performance scores of how your website is loading. Both of these tools are known as synthetic testing because they simulate users and devices. And this is helpful because as you're doing optimizations, you really want to know accurately how much they're improving, or if you have a regression, how much time you're actually losing. So the test scenario has to be dependent. On the other side, there's RUM, which stands for Real User Monitoring, and this gives you the same metrics, but on a real user device. With a small library like Perfume.js, you can get all of these metrics, and including first input delay, and you can save all of that to Google Analytics and also support any custom analytics that you might, server that you might have. So you saw some of the metrics that you can have. During the page lifecycle, there's time to first byte, there's first contentful paint, there's time to interactive, and Personally, we found that FID, which stands for first input delay, was the most important metric, and I'll tell you why. Because it measures the time from when a user first interacts with your site, example, when they click on a link or tap on a button, to the time when the browser was actually to respond to that. And the reason why we found that's important, because there's a behavior known as rage clicking. That means that when users tap on something and it doesn't respond and they just keep tapping and tapping and tapping, that's known as rage clicking. And the difference between users leaving because the site was too slow versus users leaving because the site didn't respond, we found that the first case, users leaving because nothing was shown, they're most likely to come back, but users that were frustrated because the site didn't respond do not come back because they got angry. So this metric, out of all of them, we found the most important to track. And now that you know those metrics, now you know where you stand, you can start comparing yourself to competitors. Using the Google Chrome UX dashboard, you can get the same metrics on any other websites. You can get first contentful paint, and I believe a couple of months ago, first input delay was now recently added, so you can get that as well. You can get their connection distribution, 4G versus 3G, and also device distribution, desktop versus mobile. It's logical to try to compare yourself on the same device with the same speed, but I recommend you to see where the 95th percentile is. So your competitor, most of their users might be going to a different device or a different speed than yours, so it's not accurate for you to be measuring yourself against them on the same speed if the majority of the users are going on a different device or different speeds. There's also another side, think with Google, where you can benchmark the mobile speed index. This is the aggregate of all of the metrics, and you can really quickly see where you tally against everyone else. This is really helpful to show non-technical people or executive leaders. And most importantly, they also have a performance calculator, which shows you that when you input some different variables, it shows you how much money you're potentially losing by not speeding up your site. When I was showing this to my bosses, I still had some slides left on my deck, but they stopped me when they saw this and they just told me, go and do it. So now we had approval. We had some time to go and work on this. So we have to find where is the bottleneck. There are many things that can slow a site down, but we try to find what is the one thing that we can fix and will give us the most impact. And we found that it was JavaScript. Like Liran mentioned, regex, CPU blocking. Actually, JavaScript is CPU blocking. Anything that JavaScript runs, by default, it runs on the main thread. Browsers, anything that goes in your browser runs through the main thread. And anything that blocks the main thread blocks absolutely everything. That's users clicking, users scrolling, anything. So JavaScript, if you are not careful, can block absolutely everything. And also, if we see an HTTP archive, we can see that we've only been adding more JavaScript as we go through time. The median web page has a 350 kilobytes of JavaScript being loaded on page load, which amounts to 15 seconds of time to interactive on mobile 3G. Now imagine loading something and not be able to interact with it for 15 seconds. That's the most common website in the world. And also, this is the median, which is the middle number of a total. The average, which is reflected, I don't think that you can see it here, but there's this shadow. This is the average, which is actually 500 kilobytes. So why is JavaScript different, right? Loading at 200 kilobytes of JavaScript will not, it's not the same effect as loading a 200 kilobyte image, because all bytes are not equal. Like I said, a 200 kilobyte JavaScript takes much, much longer than a 200 kilobyte JPEG. And why is this? Because JavaScript has many different steps. First, it has to download from the network, from a server. Then it has to parse and compile so the browser can understand what it does. And then it has to execute and run. And each one of these steps have a cost. So download, that's why we minify it and we put it on a CDN. But until last year, parse and compile used to be the top more expensive part of the process. 10 to 13% of time was spent on page load. And then the JavaScript would have to execute. But this year, the Chrome team has made some parsing updates. And they're able to do what is called script streaming. And this is that as soon as they see 30 kilobytes, they're able to start parsing and compiling some of that JavaScript as it's being downloaded. And on Chrome 71, they moved to a task-based approach. This means that using worker threads, they're able to run this concurrently. So as multiple files are being loaded, they're able to parse and compile at the same time concurrently. I do want to go back to this because you see that number of 30 kilobytes. This is an interesting number because as code splitting has been being given as the most performant technique that you can do, developers usually don't know how much you should code split. And you end up with really tiny bundles that are loading at the same time. And while HTTP2 loads all of these bundles concurrently, it does have a max connection that I've seen 6 to 8 connections at the same time, similar to HTTP2.1, where anything after that that is being loaded concurrently will be deferred. And now that we have this recommendation of 30 kilobytes, the recommended size to be able to take advantage of this approach while also not have other browsers be slow is to have your bundles be near 30 and 50 kilobytes. And this approach led to up to a 3% TTI improvement simply because the main thread has been allowed to be free to be able to do something else. So knowing all of this, this is how we were doing before. We had a 150 kilobyte bundle on our feed pages that added up to 360 kilobytes uncompressed. This took, to parse and compile, up to 2 seconds on mobile in 3G. And this line that you can see here, this is the main thread activity. This is really bad, because this means that nothing else at this point can happen. It's just blocking the main thread. And this added up to our load time of almost 13.5 seconds. So now we knew everything. We knew why we were slow, and we knew where we wanted to go, and we knew how we were, what were our metrics. So now it was time to make it faster. The first question that we asked ourselves is, does the user need this right now? Whatever it is that you're loading, this piece of code, does it need it right now in this second when you're loading the site? And a good starting point is to always just defer things. So there's a document lifecycle, there's document load and window load, and that's really easy, but I feel like the next step is to infer by user action. And what I mean by this is being able to track what the user is doing and kind of predict what they're going to need eventually. So we have an example on our feed pages, this infinite load feature. And what it means is that as the user is approaching the bottom of the feed, we load more items and we put it underneath. So the usual approach is that you have a scroll handler, and you track the user's scroll position, and when they're nearing the bottom of the feed, that's when you load something. But using intersection observers, you're able to get the middle element of the feed and observer. Now, you do need an is intersecting check, because this callback, the intersection observer callback, fires right away when you observe something. Now, remember that, because it's going to be valuable. Now, once it actually is intersected, we disconnect it, and this is when we load the actual code of infinite load. This is the code that is doing that AJAX request and is putting all the modules underneath. This means that on page load, that code isn't there. And if someone doesn't scroll far enough down, they never see this code. And then we set up the feed element to that module, which does a similar technique, only that it observes the bottom element with a threshold up in order to do that AJAX request. We can also do progressive enhancements. For example, we have a search modal that has a type ahead feature. What it means is that as the user starts typing, we offer them some suggestions. But when we think about it, what is the most critical thing that the user needs to do is to be able to open that model, start typing, and hit enter. At that moment, the type ahead becomes an enhancement. It's something nice to have, but it shouldn't block the user action. So we divided that function, that type ahead function, into another bundle, and we realized that in order to open the modal, we don't really need to JavaScript. We can do it just on CSS or HTML. And this allows us to be able to disable JavaScript altogether, which mimics the environment where someone is in a really slow connection. So here we're disabling JavaScript, opening the modal, and the user is still able to type and hit enter. And to do that, we use the CSS target property, which has been on the language for a while. We use an A tag with an href, which will change the URL. And then we have our modal with that ID. And then on CSS, we have the column target. And we just use a Z index to be able to move that modal from the background to the foreground in order to show it. This works on every single browser, even IE10. But there's a better way, which is a little bit modern, and you can polyfill it. We're using details with summary. Details is an HTML tag, and this is all the HTML that you would need. And this is some of the CSS that you would need. And I have this glitch, which you can go and remix it and see all the code. And on the left, I'm using the CSS target, so you can see the URL changing. But on the right, I have the modal. All of this is happening without JavaScript. It's only HTML and CSS. And the use of web workers, not to be confused with service workers, because service workers are the network side. It's what is really critical to do a PWA, for example. It's what allows you to cache a file and serve it offline. But without web workers, you're still going to run that JavaScript on the main thread. So a common weakness that I've seen of PWAs is that they need to be updated. And an update is usually additional file size. A new feature was added. And so they show a button of update. And when you update, you load that new JavaScript that now is bigger. And it runs on the main thread. And at that time, you could actually crash the browser. And that's the worst experience that you can give someone, that you are updating the PWA and you crash the browser because you're doing that. So web workers allows you to not do that because it offloads work from the main thread. Using a library like comlink, you can easily move something off of the main thread. In this example, the object app, it's in a worker thread. So when we fire do something, all of this that happens in do something, it's off of the main thread. So what are the pros? I mentioned, obviously, offload work from the main thread. But the most important plus that I feel web workers have is that you can run as many web workers as you want, and they run in parallel, and they do not block the UI. Meaning that you can have many web workers doing separate things, and they don't block the UI. Even though web workers are now very, very well supported, people don't use them very much because the people think like you should only use web workers when you're doing really intensive things, like if you're creating an image or you're rotating it or you're cropping it. But I would advocate that you should use web workers for everything. Because if whatever blocks the main thread, even if it isn't you, if it's third party, you are done. The user is going to be blocked from doing whatever they need. But they do have one downside, which is they cannot access a document yet. And I'll get that to a second. Now, we use comlink, which is a 1.2 kilobytes. And there are other workerize, or I forgot the other one. There's a couple more libraries. But whatever you want to use, please just switch to web workers. If there's anything that you take away from my presentation, use web workers today. But there's a misconception of when I talk to people about why don't you use web workers, they usually tell me this. but post message is slow, which is the mechanism that web workers use to communicate with the main thread. And I say, well, no, it depends. Earlier this week, I was very fortunate that Surma from Google did a really intensive research into the performance of post message, so I don't have to. And he found that even on the slowest device, you can post message objects up to 100 kilobytes, and you stay within your 100 milliseconds response budget. 100 milliseconds is the time where the human eye still perceives something as being smooth. Anything after that, we start seeing it as like something is slowing down. So that should be your response budget. And if you have JS-driven animations, you can have up to 10 kilobytes of payload are risk-free in order to not make that animation feel slow. Now, what I would add to this is that if you are doing JS-driven animations, please consider CSS first and add JS on top of that. And the reason why is because with CSS, you can access the hardware, so you can have really reliable animations. And also, in multiple browsers, they have a compositor thread that caches CSS animations. And you can test this by having an infinite load on your file and a CSS animation. If you have an infinite load, everything will be blocked. You can't scroll, you can't do anything, but the CSS animation will remain playing. That's because it gets offload to a compositor thread, and that's where it's just cached forever. And I did mention that currently, the one downside of web workers is that you can't use the DOM. But there's a new library called WorkerDOM that is in alpha right now, and it lets you do exactly that. It provides two files, one index, that add this main thread element that lets you upgrade an element that has a source, which would be your file. And in that file, you can create elements, add them to the DOM, and add event listeners. So in this case, I added an input tag that I detect that when I type change, I run this function that all it does, it checks that if my color is green, I switch it to red, otherwise I switch it back to green. And this is how it looks. Now, this is obviously a really trivial example, but mind you, all of this is happening off the main thread, meaning this will never block the user. After doing all of these optimizations across many different bundles, this is how we ended up after. Our bundle went down to 9.4 kilobytes, which is 27 kilobytes uncompressed. We didn't take advantage of the 30 kilobytes there, but we did this before Chrome did that optimization. And now it's loading at 220 milliseconds. And you see these little blocks spaced out. This is beautiful. This is what you should strive for, because see, in this space, anything else can happen on that space. The user can interact, other scripts can load, anything can happen. The main thread is free to do whatever it needs to do. And it bundled up to that sweet time that we were looking for, 2.5 seconds. This is when we're able to show the user something that is valuable, so they can continue and decide that the content is valuable for them to remain on the site. To put that in context, that's 4 seconds faster of first contentful pane. This is how we were loading before. We don't see something until about 6.5 seconds. And then we're finally loaded at 13.8. And this is how we were before, after. At 3.3, we're visually complete. And this made it clear that we needed to work on other optimizations. So for example, we see that at the beginning, we only see this a pink rectangle and not the fonts and everything. So we were able to do more smaller optimizations, like adding a background with a CSS loader to improve that perceived performance. But there was a difference here. This is all page load performance. And there's runtime performance, meaning after your page loads and the user starts interacting with it, that's runtime performance. Our runtime performance was still pretty bad. And so to our bosses, everything is just one thing. Everything is just, why is the site still slow? Sure, it shows up fast, but I still can't interact with it, or it doesn't react as fast as I wanted. And to talk about this, we need to talk about first party and third party. Like I mentioned, first party is everything that we can control, and third party is everything that we can't. This is a web page test waterfall of that 2.5 seconds, and I broke it down in colors. The first part are 11 requests. First party, these are the resources that we control, our fonts, our CSS, and our JavaScript. Then our tag manager, which is what controls all of our third party, loads on the 7 requests, and it loads our third party, which loads 125 requests. Now, besides the amount of that, or whatever those scripts are doing, the problem that we have is that we can't tell where all of these third-party scripts are coming from, because it all happens on the fly. It all happened there. If you're not familiar with header bidding, everything gets sold right away as the page is loading, because that's when it's tracking what the user is, where they're coming from, what language they speak, in order to deliver the appropriate ad to you. So when our leaders were asking us, why is the site still slow? The answer was pretty clear, that it was that. So this is something that we're currently working on in order to tackle this, because it's not as easy as saying, well, just remove it or defer it, because third party is what is giving us money. And that was the main thing that we convinced our bosses, saying that by making our sites faster, we're going to make more money. So we couldn't just contradict ourselves and remove third party that would directly affect our revenue. So this is an approach that we're currently experimenting with. We use a Lambda function to load our sites with a query parameter called third parties. And it performs as regular. Our tag manager loads all of our scripts. But we track, so we give our Lambda function, using Puppeteer, the list of what we consider third party. Anything else but outside of that is third party. So what it does, it collects all of those resources and uploads them to S3. And at the same time, it stores all of those references on Redis, but you can use any in-memory DB. And then, when the real site loads, all the users are still loading all of these files, but they're coming from our servers, because that means that we don't have to open all of these connections to 125 different domains. We can just load them from one domain. And this opens the door to any number of optimizations that we can do after that we store them, because, for example, we can run a regex of saying if there's any document.querySelector code in that file, and if it's not, we're able to put it on a web worker, for example. But for now, simply doing that optimization of loading everything from one domain, we're seeing up to 20% improvement. And now, either on content invalidation, when this page changes, or at a scheduled time, be that every hour, we trigger the same function, so we do all the process again, so we can update our ads or update our third party. Now, this is important, like I said, to speed your site up. But I'm going to talk about how can we make it stay fast. And to that, we have to talk about how can we include it in the development process. Performance is huge. There's so many different things that you can work, and we decided to divide it on 3 main categories. The server, which is API request and CDN. Application, which is HTML, CSS, and JavaScript. And development, which includes our build CI speeds. And each one of these have potential bottlenecks. This is a comprehensive list put together by Paul Irish that lists all the things in JavaScript that are render blocking, and it's a lot. And so when you're learning all of this stuff and you're bringing it in to your colleagues and you're bringing it in during reviews, it can be pretty overwhelming for everyone, because it means, well, what do I do if I can't use any of that? And I found that the better question to ask is, what do you intend to do? What are you trying to do? Because we shouldn't demonize all of these properties, because they're all valuable. And the more that we ask this question, we're able to abstract frequent optimizations and not just say, no, don't use that. And I wanted to talk about GetBoundingClient rect. Who here is familiar with this method? Great. It's an amazing method. It has been in the standards since IE6. And what it does, it gives you the top, left, bottom, and right positions of an element, regardless if it has position relative or static or fixed. And it's the most precise. But there's a problem. It was in the list, so it's bad. And there's a way to get around it. Using request animation frame, you can defer when you actually request that animation. But there's a problem. If someone else on a different file is also having a request animation frame that changes the size of the same element by adding a CSS class, then the first part is as bad as not doing, because it will still go back to the render steps in the event loop. So do you remember when I told you what happens when you observe an element and the intersection observer callback fires right away? We can take advantage of that and see that the entry, when you observe something, has this information, has the BoundingClient rect information right there. So knowing this, we're able to write our own asynchronous GetBoundingClient rect that on the fly creates an intersection observer, gets the entry, the first entry, because simply we're observing one thing at a time, and it sends you this BoundingClient rect. So in your code, you wouldn't write a header or element GetBoundingClient rect. You would await on that function that you created where you pass the element. And this is what I talk about performance culture. A developer doesn't have to know why this is better. They just need to know that this is what they need to write instead of this. And the more that we start developing those patterns, the more that we can make performance last. Another very quick optimization that we do is that on the background, we automatically switch all of our clicks to touch start. That means that developers can still be writing click, and automatically when users go to our sites on mobile devices, it feels up to 100 milliseconds faster because everything reacts on a touch start, which is when you press down, versus the click, which fires when you press up. And now, I did mention the number 100 milliseconds, which is very minimal. So developers usually ask, is it worth it? Do I need to go back and fix my code in order to achieve this? So we drafted 3 different questions to when performance should block the development. And is it part of the critical path? And what I mean by this is, whatever code you're writing, is it happening, is it executing while the page is still loading? And if the answer is yes, you should address performance. How frequent will it run? Do you have something that you are getting from a data and you're running a loop? You don't know how big that data would be. So your loop, whatever you're doing on that loop, should be as performant as possible. But this also addresses having an interactive component. For example, a date picker. I'm friends with people that work on airline websites, and you know that when you're trying to buy tickets and you are not sure if you should fly the Thursday or the Friday, you keep checking and clicking around, and if that element is not responsive fast enough, you're going to get frustrated. And the bigger question that is not measurable is it a share or a base component? And what do I mean by this? When developers write things, they tend to get really focused on just writing that code that fixes that specific feature. But we have to know that whatever you're thinking that is only addressing one thing is going to be seen by other developers as a pattern, as something that can be reused and extended. So we need to think of whatever code that we're writing as what else could be done through this code as we're putting it in. And all of this, let me see that we're really planning for today's problems. We're building features, we're building a code that addresses today's features, and we're not really thinking, where do those features go? So how can we prevent from blocking ourselves tomorrow? Which led me to a third path that is usually not talked about, of product and design. This is our life cycle. Someone has an idea, then we build a prototype, then we test that prototype. If it's successful, it goes into development. Then we determine a minimum viable product. What is the minimum thing that this feature needs to do in order to be successful? And then we optimize. Now, in most companies, this is where performance happens. We wait until there's a problem, until something is noticeably slow, and then we fix it. And this is where I thought the performance should happen, because anything before here, it's not real. Like, we're just experimenting and we're testing. But then I found this is where it should happen. And there are a couple of reasons why. For us, we were building prototypes so fast that we're successful and people liked them, and then it would go into actual development. And because the prototype was built so fast and so hacky, it just took so much longer to build the actual real version that non-technical people in leadership felt confused. Like, I just saw this, like I was playing with this. Why are you telling me that now I have to wait a month or 3 months to see it actually live? So that was one problem. But another problem is that since we were only asking the questions of what this feature does. We were not asking, how could this be reused by something else, right? And the question that I found that it was the most helpful is asking ourselves, whatever we're building, what if it rocks? What if it's amazing? What if it ends up being the most popular thing for revenue or for the product? How do you see that feature growing if it is successful? And asking those questions helps us address from the code, from the very beginning, how would that code grow as that feature becomes more popular? It lets us draft performance paths. We ask, why are we doing this? What is the goal of doing this? We can align best practices with goals, and we're able to say, if we're doing something for SEO, we should watch out how the render time is affected. Or if we're doing something interactive, we can look at the runtime performance. And we also can compare mobile versus desktop. Desktop devices have more of a performance capability. So if you're able to put something together without addressing performance that much, test it first on desktop, and then later you can move it down to mobile if it was successful and add all of those performance optimizations. And we document our trade-offs. We can specify the reasons. When you make a trade-off, you're making a trade-off either if you know or you don't. We make trade-offs every day, and the more that we try to know what the trade-offs is, the better we're going to be. So if we document it and we ask ourselves, what are the trade-offs that we're making, and is it by design? We're making that trade-off and not adding a library because we are making that decision today. Or is it a technical limitation? Is it something that you wanted to do? For example, you wanted to use web workers, but WorkerDOM is still on alpha. So you're able to document that, and when WorkerDOM is out of alpha, you can do a search on your documentation and go back and see, oh, hey guys, we can actually fix this now. And having that documentation lets you plan them. Something really helpful for non-technical people is to describe the scenario that a trade-off would block. If you tell them, hey, if you envision this feature eventually being able to do this, if we don't do this right now, it's going to be much harder to do that later. That's a really helpful example to show to leadership of why we should address something today. And overall, it just really prevents told you so moments between coworkers. No one likes being told, hey, I told you that if we didn't do that, it was going to be bad. See, I was right. No one likes being told that. So the more that you just document it, the more that you prevent people from really getting their feelings hurt, because it was on paper, we agreed on it, and it's there. But the bigger question that I wanted to answer today was, how do we stay fast? Performance budgets are great, but it's rarely a single pull request, right? Like our problem was we have developers adding 3 kilobytes of JavaScript, and they say, well, it's fine, right? But then you add all those up, and it ends up being 300 kilobytes at the end of the week. So I thought about how can we predict regressions? And I built this tool called Spotter a while ago that it has nothing to do with performance. It just tells you if there are any other open pull requests that are working on your same files. And I thought, how can we use that and start integrating on our CI? So I thought about Spotter CI. And what it does is that daily at a given time, so for us it's 8 a.m., it goes and collects all of the open pull requests that have a ready-to-merge label, for example. And what it does, it merges them into a temporary branch, and it opens a pull request and assigns any users that you have given it through a configuration. That means that at 8 a.m. every morning, I can answer the question, how bad is performance if all of those pull requests are merged today? But there was a problem. There was no tool out there that would give me the consolidated performance on a pull request. So all of them, all of the tools that I tried had problems. Had a single URL, it ran and blocked the build process, and it had no consolidated reports. So what to do? Well, I built one. So I'm happy to introduce this tool that I released this week. It's called Lightkeeper, and it lets you maintain Lighthouse budgets in pull request URLs. The way that it works, it runs after your CI. Who here uses GitHub? And who here uses any of these tools? And if you don't use any of these tools, you can use any GitHub check run deployment or status. Pretty much anything that shows here, Lightkeeper can run after that. So if you have anything Jenkins or something else that is creating a pull request URL, Lightkeeper is going to run after that. It has a flexible configuration where you can say performance scores and Light Wallet, which was introduced this year by Google. So you can set budgets on your script or third party, and routes for homepage articles. And you can customize the settings per route. And this is a really custom one. You can customize everything, even the Lighthouse settings. So you can load one URL on desktop and one URL on mobile if you wish so. And this is how it looks. It tells you all the errors that were found across all the URLs, and it has drop-downs, so you can go deep as much as you want. It also has warnings, so you can get on top of refactoring. And this is how it looks with performance budgets. It can tell you how much over budget you are over resource counts or resource scripts. And this is the only comment that it adds. It has a consolidated report that has warnings and errors. And if you have improvements, you see those at the top. So that way, if a developer is accidentally making an improvement, they're able to see it right away. And so try it out. Here's the link. I'm more than happy to hear what you think of it. It's pretty early. Like I said, I released it this week. So I'm more happy to see if you have any ideas or you would like to see any other features added to it. And the main reason why I'm building this tool is because I think that performance culture is more than code. You can have the slowest site or the fastest site. That doesn't mean that you have or don't have performance culture. Because it's not about fast or slow, but the choice to wander out and tackle priorities that you might have on your business, but to have that clear path back to where the site should be. Thank you so much for listening. I'm on Twitter if you want to follow Lightkeeper or Spotter CI, which I'm currently building. This is the URL if you want to see this deck and all the URLs on Glitch for the code. And that's it. I'm going to be at the speaker corner or at the party. Just come grab me. I have Lightkeeper stickers.
Yeah, who would like to take more stickers about Lightkeeper? Please find Alfredo in Speaker's Corner. And thank you again.